So today's content covers math concepts, significant figures, trig functions, as well as vectors. So the objectives, we're going to learn the common Greek alphabet characters. We use those quite a bit. Explain the importance of significant figures, be able to identify the number of sig figs in a measurement, be able to report data to the appropriate amount of sig figs, identify the types of error that may be present when you make a measurement, and know and apply the standard trig identities. So the Greek alphabet. In math, science, and engineering, we use this a lot. We use a lot of symbols to denote various quantities. And a lot of times it's the default symbol and it's out of the Greek alphabet. So it's very handy to get to know your Greek alphabet. So I'd like you to learn these. There's a couple of little songs here, might help it sink in a little bit, but in particular, to get started, let's memorize at least the first 6 letters in uppercase, lowercase, and what the name of it is. Okay, so moving on to significant figures. Anytime you make a physical measurement, you can't make it exactly. At some point, you are making an estimation, okay? Whether you're reading rain on a rain gauge or temperature on a thermometer, at some point you're estimating. So the need for sig figs arises due to these measured values because the sig figs are what you use to communicate how well those values are known exactly and what part is uncertain. Okay, so the more sig figs you have, that means you have a higher degree of exactness or accuracy in your measurement. So when you present a measurement to a certain number of sig figs, the underlying communication is that the value is known exactly except for that very last digit. That's the one where the uncertainty is. All right, so you want to be careful. If you say you know something to 2 decimal places, for example, so 3.14, that means you know it's 3.1, and then on the 4 you got a little bit of wiggle room. If you just write an answer on your paper that you dump out of your calculator, so it's 10 figures, you're communicating that you know that all the way down to like the millionth decimal place, and that may not be accurate. So be careful when using sig figs. We'll work through a few examples. So there's some rules when determining the number of significant figures. If it's not a 0, then it's significant. Rule 2 is about captive zeros. So if you have zeros trapped in between numbers, then those are significant. So 2004 has 4 sig figs. 105 has 3 sig figs, the 1, the 0, the 5. Now, leading zeros, if they're at the beginning, you don't count them, okay? They are not significant. If I look at 0.22, this leading 0 is not significant, okay? The 2 sig figs are this 2 and this 2, all right? So note also that we did write this 0 here, okay? This guy's written here because if you just write 0.22, it's often very difficult to tell if that's a decimal place or if that's like a speck on your paper. So if you put that leading 0 out in front, it clarifies the communication that this is 0.22. All right, similarly, this guy has all these leading zeros. All these leading zeros are not significant. This has 2 significant figures, the 2 and the 2. Trailing zeros are different. Trailing zeros are communicating that you know that to much more accuracy than just the number itself may indicate. So the trailing zeros are important. Now, if I look at this, 200, okay, without a decimal point here, then 2 is the only significant one, technically. But a lot of times we write 200, but we mean we know it to like at least the ones place. So to clarify that, put a decimal. Because if I write 200 for 200 with a decimal at the end, it now has 3 sig figs. And that means that the only uncertainty is in this lowest digit right here. Okay? The previous example, it looked like my uncertainty was in this 2, so it was like plus or minus, 50. And so that's not really what I wanted to communicate. I know the value closer than that. So always be careful about your decimals. And this can also be tricky because what if it's at the end of a sentence? Is it a period or is it a decimal place? So sometimes communication is difficult. We clear it up a little bit. This guy, 200.0, has 4 significant figures. This means I know it all the way down to where my only uncertainty is right here. So all of these are significant. Similarly, this guy has 4 significant figures, but this is a leading 0, so it's not significant. It's these 4 that are significant, and I'm communicating that I know it all the way down here to this 10,000th place. All right, rule number 5. If a number is exact, we assume it to have infinite significant figures, okay? Because sig figs are used to indicate where your uncertainty occurs, and if a number is exact, there is no uncertainty. So we say it's an infinite number of sig figs. Numbers that you get by counting are exact, right? So if you're counting cows in the pasture and there's 7, you know there are exactly 7 cows. There's not 7.2 cows, there's exactly 7 cows. If you're counting coins laid out on the table, you know there are exactly that many coins, okay? So those are exact. Some conversion factors are exact, like there are exactly 12 inches in a foot. There are exactly 2.54 centimeters in an inch. Those are exact, they're not approximated. Sometimes writing something in scientific notation will help clarify the number of significant figures. So that confusion that we had previously about 200, is it 1 sig fig or is it 3 sig figs? Well, you can clarify that by writing scientific notation. If I wrote it 2 times 10 to the 2, this has 1 significant figure, so it has 1 significant figure. But if I write 200 with a decimal, I'm trying to communicate 3 sig figs. I can do that a little bit better with scientific notation if I write it 2.00 times 10 to the 2. So you don't worry about the times 10 to the part when you're looking at how many sig figs you have. It's about what is this number. And I wrote it with 3 significant figures, so it has 3 sig figs. This guy, I could clean up any confusion by moving my decimal place over here and writing it as 2.2 times 10 to the minus 3. Okay, this guy has 5 sig figs no matter what. But if I were to write it in scientific notation, I would move my decimal place 1, 2, 3, 4 units. So it's 1.2675 times 10 to the 4. Okay, so let's talk a little bit about the subtle difference between accuracy and precision. So accuracy is actually a measure of how close your value is to the standard or to the exact value. This means you need to know the exact value, okay, but that's what accuracy is. How accurate is it? So if you look at this picture over here, right here, I am hitting the bullseye on this thing, right? I am very accurate. I know where it needs to be, and all of my measurements are pretty close to where they need to be. So that's accurate, all right? Precision is slightly different. Precision refers to how close are multiple measurements to each other. So is the measurement repeatable? So in this case, you can see I've got a high level of precision because every time I do it, I'm hitting the same spot. Okay, every time I take a measurement, I'm getting the same value. However, it's not necessarily accurate because it's not right there in the middle of the target. This guy is both precise and accurate. So this is varied definitions of precision and accuracy. You can see this target down here, I'm neither precise nor accurate, right? It's just scattered everywhere. So when you got a lot of scatter in your data, it's not precise, it's not accurate. We use those words interchangeably quite a bit. Just be careful about what you're communicating when you use the word accuracy versus the word precision. So anytime we make a measurement, it's automatically going to have some error associated with it, unless it's an exact count like counting the cows. The number of sig figs communicates the amount of error. So if I record a temperature to 51.0 degrees Fahrenheit, the only uncertainty is in, I'm kind of estimating in this decimal place. So I'm only estimating in the tenths place. And there's two types of error that we can generally encounter in scientific and engineering measurements. Systematic errors are errors that tend to shift the measurement consistently in the same direction. And you can typically identify these, right? And you may be able to correct them. So let's say, how many of you in your garage at home have a tape measure that has the end broken off? So when you make a measurement, you just sort of account for that, right? You can't find the end. You're never going to reattach the end, but you can account for it. Okay, so you can't correct it, but it's identifiable, and you know you just add an inch to every measurement you make. Sometimes in the chemistry lab, you'll find a blob of something on the scale, right? And you're trying to measure the mass of something or the weight of something, but you've got this foreign matter on the scale. If you can get it off of there, then it's correctable. But if not, that's why all of our scales have that zeroing mechanism. It accounts for stuff that's already there, and you can start your zero baseline, including the blob, so we can account for it. Random errors, on the other hand, are things that sometimes they're a little on the high side, sometimes they're a little on the low side. They fluctuate from measurement to measurement, but it might be in any direction, okay? Even if you're using the same device every time. So random errors are those that are kind of accidental. You can't really identify them, you can't predict them, but you set your experiment up as cleanly as possible so that you at least have as few of these as possible. But you may not be able to get rid of all of them. So for example, whenever you have a human that times anything, let's say they're timing a sprint race. Well, when people cross the line, you're going to click it, and it's not going to be exact every time. And sometimes you're going to jump the gun a little bit, click it a little early, click it a little late. Any human measurements have a random component. You just cannot avoid that in the humans. All right, let's shift gears now to trig functions. This should all be a review. I hope you had this math previously. If not, you should be able to pick it up here. We're going to talk now about right triangles only. Okay, so when we're talking about these trig functions, sine, cosine, and tangent, they only apply to right triangles. When we're talking about Pythagorean theorem, it only applies to right triangles. So when I have a right triangle, right, I've got one angle that's 90 degrees. So if this side has a length x and this side has a length y, then I can define a few things. When this is a right triangle, of course we use the little square to indicate that this is a 90-degree angle. And so for this angle over here, which we're going to call theta, see there we're using that Greek alphabet again, sine of that is going to be the opposite side divided by the hypotenuse, right? So y over r. Cosine of this angle theta is going to be the adjacent side divided by the hypotenuse. And then tangent is just opposite over adjacent. So those are here, and that's where that SOHCAHTOA thing comes from. You'll all probably know this, but sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. Okay, and then by Pythagorean theorem, the length of the hypotenuse, which is the side that is opposite the 90-degree angle, is just simply r squared is equal to x squared plus y squared. Now we encounter some common angles, and so I want you to learn these, and I want you to be able to tell me the sine and cosine of each of those. Now sometimes the picture is helpful, okay, so that you can remember sine of 0 is 0, right, if you can remember this picture. And really, if you can remember just one of these, you can recreate the rest of them. But this is for 0 degrees, 30 degrees, 45, 60, and 90. You also need to be able to convert to radians. So there are pi radians in 180 degrees, right? So if I multiply this by pi over 180, pi radians per 180 degrees cancels the degrees, and I end up with pi over 6. Okay, so make sure you can convert between the two, and we will practice this. But for the angles of 0, 30, 45, 60, and 90, convert them to radians and be able to determine sine and cosine. Note the pattern here. Note what the function looks like. Sine, for example, it starts at 0 and it increases up to 1, and then it decreases, and then it goes back. Okay, so as I go from 0 to 90, which is right here, pi over 2, this should be going up. So it goes 0, 1/2, square root of 2 over 2, square root of 3 over 2, and then 1. And if you break these down a little bit, this is kind of like square root of 1 over 2, square root of 2 over 2, square root of 3 over 2, square root of 4 over 2, because that's going to be 2 over 2, which is 1. So if you can remember where 1 starts, and remember the fact that they look like this, right? Sine is increasing from 0 to 1 as we go from 0 degrees to 90 degrees. You can generate this. The cosine graph starts at 1, and by pi over 2, it's down to 0. So it's the same values, it's just reverse order. So you've got cosine of 0 is 1, cosine of 30 is square root of 3 over 2, square root of 2 over 2, 1/2, 0. Okay? So that concludes today's material. Thank you for watching.